Let's begin. So, welcome everybody, big class, uh, to this workshop for the math for making cool things appear on the screen workshop. Uh, I am presenting this for GPK, and first I would like to say, uh, why math? Math is so dumb. That's what I said in high school, uh, where I learned a lot during like school and whatever when I was a kid, but I felt bored on it, where I basically just wanted to um, not care about it, and I and whenever I got to college, I basically got to the point where wait, to the point where basically I just wanted to do something more in math where it's more visual. And I think that with graphics and machine learning and the video games, I think it's a great way to like get into that point. And I think that the biggest thing is for games, as you can see here, we have the characters on the screen. Wherever you have a headbutt, you can have like a vector for math and have it like interact with different aspects of the game where it can launch you. For example, the headbutt is from Smash, where it just hits you up the the top. And for example, the bullet, you can put it like it's kind of like another vector. It's like a dot product where you can see the camera come down here, and also where it releases continuously, and you can see. Oh wait, my screen is over there, and you can see transformation like how it moves in a game. Um, as for who I have here, machine learning. So everybody has TikTok or Instagram or a type of short form content where you can see recommended videos like that, or like a Reddit story, or like a Minecraft video where it's just telling something. For machine learning, it's a point where it's taking your information in and gathering, like getting your your matrices and storing the data set on, for example, the kind of like assess what you are as a person and how you can you can see your projects. And for example, I have there my YouTube recommendation page where it's just I have here my Nick code. For example, a Nick code video, this album, which by the way you should listen to. This is a really good album. And yeah, it's basically getting to know like how is this the right prediction? I think that's the biggest takeaway for math in machine learning. You can hear my laptop over here. uh, as for graphics, um, this one is more into inspiration of mine, where you want to have the where to place the objects, where can I see the light, where is the camera moving, and you can also see it over there with the vectors and direction of light. For crossbow, you can also see the how a coordinate system is built and how the for matrices you can transform into a 3D into a 2D space. Yeah, and I think that it's good for that to get into the next session where we are talking about vectors and products, where basically uh, one thing that I need to get into. I really hope that you like the vector reference over there. Um, yes, you love that guy. For vectors, one of the things that I my dad has always says, he's a electrical engineer, is that he sees a lot of vectors like in his daily life. For some reason, now I started to see it too. where basically I kinda get into the mindset, for example, in games where I can see a better happen on like a screen, like visually on on my mind. And for computer graphics, it's important to actually see how a light is taking on the environment on like a character or camera or something like that. And for machine learning, um, it's insanely good to actually represent the data set on, for example, the something is represented, like for example the age or the gender of something, where you can get the um you can get a closer look of how accurately represented something. For that, now let's have dot product and cross product, which is another subsection of vectors, where you can see the fundamental part of theory here, where basically um, there's a lot of great techniques that you have here. One of them is called ray tracing, which you can see the picture over here. It's basically getting the kind of similarity of something, and you can actually place the light onto it, and where you can see the light over here kind of get like a reference over here and display it perpendicularly. And for dot product, this kind of more general example, but for dot product in machine learning, it's also a great way to assimilate the perpendicularity of something, like the similarity of something, because something's perpendicular, it's more separated. And you can also see for cross product is how something renders on the screen. Uh, and now, well, okay, let's go something cool. This example is like making. Was it not playing? Oh, yeah, it is playing. It's like a DVD where you can see the more effects of vectors, for example, and kind of get into the mindset of utilizing vectors to actually code something cool. And if you guys have your laptops, you can go here. I'm also gonna put this on the Discord for the math section, on the math channel, where basically this is kind of like getting into Shadowtoy, which is just for making shaders. You can click on this link. Let me go right there. I put this Discord. Oh, so you. Okay, thank you. Yeah. Hmm? You can put a math channel something. Where is this? Yeah. Oh, it's running. Oh. Oop. Okay. So, is everybody there? Yep. Okay. So, how do we start this? First off, I would like to make kind of like a circle over here, where I want to have the kind of like a round, and I'm gonna start over here. To start a circle, I have a float circle where you have a function over here. You create the UV over here. The the sound of the laptop is calling me. We have the radius. We have the blur tightness over here. Actually, let me reload this just in case this is not loading. Because Share does things like that. But yeah. Now after that, I want to have the distance that you can have on this on this example, you have the length of the TUV is basically getting into the range of the screen, and um, where you want the actual distance of the circle to actually be placed. And then return this is a cool function that um, ESL has, where basically it grounds the the function that we're doing right now, which is a circle for and distance. And then yeah. Now I again I explained UV where it's basically getting into a range where you can actually have. Actually, let me do first the velocity for this. I forgot about this velocity where you want the the vector to actually be kind of like this to actually hit the screen to move, and then you have velocity equals back to this, and yeah, I just put a random value. Now we start on UV, where I think this is the biggest thing for at least I provided the example for this on the other example that I'm gonna make, but for this we are making the UV equals fracor fracor dot I resolution, where you get the resolution on the actual scene that you want. Like getting on the range of this. Uh, and for this right now, it's like making it really be in a kind of separate way, where you don't want this to actually be affected. So what you do right there is to actually have it where it's normalized in a sense, where it is now in 2.0 minus 1, where the screen is actually the range and the domain is actually in 1 and 1 over here. And now for the actual um, drawing, we have screen up.x is the eye resolution. Oh, eye resolution. Are you guys okay with coding this right now? Yeah? Okay. Now let's actually move this. But first, we actually I forgot about this the radius of the ball that we have right now. Radius equals 0.15. Yeah. Oh yeah, and the aspect ratio, of course. The aspect ratio that matters over here, and it's basically this kind of in a sense where you can actually get the screen to actually have it more normalized. Uh, Float aspect equals resolution. Uh, Resolution dot x. I cannot spell. Help. Now let's actually make the bounds or of this. Uh, what first I need to do is to get the minimum bounds of the screen, which uh, on this example would be like on both would be -1 and 1, and for both sides of the S-plane, where now you want to have it like this, kind of like a vector over here, plus ratios, and of course you don't want the to completely have it like a -1 or something because you have to take into consideration the radius of the ball, where of course that would be bad to go off the screen. And now minus zero point 0.1 plus radius over here, and now the maths would be almost the same thing. Maths bounce back to this plus radius minus radius. Okay, so after all of that, I forgot about the range, of course. Range, uh, just this. Back to range equals max bounds minus mean bounds. And now let's actually move this. So uh, this is actually a great way to actually see how time function in this. What was it loading right now? Uh, Now where I want to do is to actually move the thing, and we have the raw position where it's gonna be like every single time, like you see the timer here. It's actually gonna take off that. It's gonna take the velocity and the time. Time, and now we have to take into consideration like uh, the bounce on the screen, where of course this, if it were going to more time that it allows for the screen, it will go like fall off or something. Now we have to consider that. This is one of the kind of like weirdest part of the code, I'll be honest, but it's a great way to see how this is bounded. And for this, you actually use the mod function that you learn in CS1 or something like Intro to C, and where you get the mod, and then you take the raw position and min bounds. Yeah, sorry for this long part. Oop, range times 2.0 minus range. And now let's actually move the circle. So uh, let's take the drawing to move moving UV where it moves the screen, and the have it like screen UV minus the position that you are actually getting this from this position, uh, and of course the aspect ratio that we calculated earlier on the position, because what it does for this one is that it takes the kind of like square in a sense, where you don't have it on like another track position the y. Oh, oh yeah, no, I forgot to show how this will look right now, but because there's like one line of code left, I'm just gonna do that where it's actually making the circle over here, where it's coming back uh, from this, and then you take this, and then the radius, and the pixel width. The pixel width. Oh yeah, no, I did not do pixel width. Over here, where it's basically getting the actual blurriness of the object. And to get this pixel width, uh, let's- I resolution dot y, and there we go. Oh, um, pixel width, and then you make it like an actual for the RGB, which for this vector 4 is kind of like making it in RGB form, and now you can actually have this be kind of like be seen on this, where it's now back 4, back 3, and you have it like that, and it should screen UV. Oh, uh, just UV black color. What am I missing? Dimension mismatch. What am I missing here? Could be for component. Oh yeah, sorry about this. Right now. Uh, High for component. Oh, back 4. Now it should run. Why is it not running? Set for color. Oh, yeah. Oh, yeah. But huh, what did I miss here? Weird. Uh, UV by the aspect ratio. Oh yeah, yeah, yeah. UV. Yeah, yeah. UV aspect. Yeah, put this. Yeah, yeah. Sorry about this. Yeah, it happens. Uh, yeah, debugging session. Let's go. Yes. Yeah. Yeah. I think what I missed here. Hmm. Yeah. Yeah.
And is
No.
it because aspect is high resolution dot x over dot y, but then you're multiplying it by the same thing again?
Uh. Oh. Yeah.
Like squared. So you're doing
Yeah,
u
yeah,
dot
yeah.
x times.
Well,
Oh, and you're also saying it equals 2, so you're actually, it should be times equal.
oh yeah, yeah,
It
yeah.
shouldn't be equal to 30
What?
on line 20.
920. Yeah, should be here.
And then that's, you have like, you're doing it twice. So
So
just use aspect to actually do your
yeah,
earlier.
aspect.
And use, yeah, use aspect later. There we
There we go. Yes. Thank you guys.
go.
You have it right there. Uh, whoop whoop whoop. Yeah, awesome. Now back to this. Uh, whoop whoop. Let's present right here. And yeah, here's the final code.
Yeah, so in that links for it, you can find
Yeah. Oh yeah, the link you can find the actual final
the
code.
file.
Yeah. Now for this we have the matrices and transformation section. Um, one of the the biggest things alongside vectors is matrices, where it's basically like a backbone on the things that we see today. They're actually extremely well mannered in a sense where they actually permit to actually move stuff around and to actually get data from, uh, kind of like in an organized manner. And one of the things that I like to do for this is that uh, for this actually really useful in security. For example, for networks too, where it's basically like a good way to connect a lot of stuff. Uh, for another thing that is really great for computer graphics is to actually visualize an object, to actually get the object to move around, uh, to to have it like a sense of being um, a great way to actually move stuff around and getting the stuff that you want. For machine learning, it's also a great way to see what biases you can have on things, kind of like vectors, where it's a great way to see kind of like where are you placed on a thing, like are you placing the vector right there, and you can see this awesome image where it's kind of like why do you need uh, a 2 by 2 matrix. And one thing that I think this video explains really great about matrices and all that stuff is a topic called homogeneous coordinates. It's a great video to watch if you want to get more into computer graphics. And yeah, I would definitely recommend. It's basically getting into 4D dimension for 3D, kind of like making the thing that I talked earlier for matrices, where for graphics, where it's making the 3D into 2D, is kind of like same for this, and I think it's a great way to actually see how it happens over there. And for transformations, you can see with transformation where the the code actually fails, not fails, but bugs. And you can see it like more visible in a sense, where for example in one of the tabling events that we had for GPK, me and Alex over here, we're tabling for a UCF event, and basically he wanted to kind of get uh, a visual to the audience, and basically what he says to actually begin coding something up. Well, I just put something on territory like I showed, and I think that uh, one of the biggest hurdles that we had is making the code actually spin, because it was a spinning cube where it had a shader and stuff, and we took a lot of time, and his battery died. And basically what happened is that even though we wanted to do that, you can see the transformation that happened to a code that actually made the the code actually work that way. And I think that one thing that it's essential for this is controlling the behavior of the system where it's actually getting into the coordinate systems. And these are common transformations where you see the, for example, algebra and whatever. These are also applied to matrices and whatever. And I think these are pretty cool. And you can see the being placed right here and there. And for now, let's go the another cool thing that we have. Um, it's kind of like a basketball, where it's basically getting an example where you can create a lot of transformations over here. And one thing that I like about this is that um, it was a great way to actually show also another aspect of math, not math but physics, because this will have a gravity and whatever else on the energy that you lose on something. And I think I really like this example. I wish we had an example for matrices, but could not think of any for that were in 3D. But yeah, I think this is a great example, I'll be honest. And yeah, let's, it's also on the same page over here. Um, that is also pulled into Discord, right? Mm. And yeah, we have it right here. I wanted to keep the functions that we saw earlier over here for the circle and the image and whatever else, and just wanted to go from there. Um, Now the another thing that I wanted to have is the mm, well, actually I have the code. Do I have the code over here? Uh, Actually, yeah, I do have the code. Yeah, awesome. Yeah, I just have it right here. Now let's start with this. So for physics, can everybody tell me the physics for Earth? Yeah,
9.8 meters
good
per second.
job. Yes. Gravity. Gravity equals 9.8. And this is something that I looked up because I wanted to do this example is the amount of energy that a basketball loses when it bounces. Apparently it's 15%, so let's stick with that. Um, Bounce loss where it's basically losing 15%, so it will be the 85 or something. And then we make it so that the ball bounces from here, from the center, and have a float start height. And now that we have this out the way over here, we can actually begin with the actual blur and the width and whatever. Actually, we have width over here. We can start with the time, where again you want the time over here to actually see what time you're getting on the float height, start height, and the velocity. Float equals velocity. Actually, yeah, you know this. Yeah, because it's not right now, not bouncing, so it will change eventually. And then you have the y axis being changed, start height, Is everybody okay with this right now? Okay. Now, uh, this is kind of like a territory thing that it has where basically if I end the program, it's gonna reset to the initial position. And what I want to show is the actual ball bouncing, where um, you have a for loop over here, because when whenever I first tried doing this, I did a mistake where I did while running, and of course you cannot do that because it will keep running. And yeah, that was bad. It was an infinite loop, which I should not have done, and it almost crashed my computer. But and that's why I do a for loop here. And here we'll have the, actually let me put this float fall time. This is gonna like getting the amount of time that you actually lose over here. 2.0 times height divided by gravity. And now we can actually see if the fall time is greater than the time that we have right now. Um, to actually see if um, the height must be changed on this example on uh, fall fall time. Now we have it there. Have it y equals height minus this gravity then time square. And now that the fall time is done, you can actually get it for to subtract the time that you have over here, fall time, and see where the velocity is actually calculated again for gravity times the fall time, where you get again the actual uh, where you want it, where the velocity is actually happening. You can actually calculate the bounce loss, where is getting the velocity to lose some of the kinetic energy that it once had, where it's just the 15% bounce loss right here. And now the height changes to actually go up again, and the velocity is times, actually, yeah, times time minus this times gravity, because it's going up, and then time up times square. And you break whenever gee, I forgot to put the break here, not that I see it at the code. Whoop. And now we have it so um where am I here? Yeah. Oh yeah, I forgot about a lot of stuff. Velocity, height, height equals velocity, velocity, uh, velocity square divided by 2 times gravity, then t rise time. Gravity. Let's go. Is everybody okay with this right now? Okay. So now that I did that, let's have the if statement where the time is actually getting into the rise time. Rise time, and you get the y velocity. Uh, right here. I don't know why I put this here. I forgot about a lot of stuff. And break. Oh, now you can see the time minus the rise time. Rise time. And let's center the ball right here, where it's basically just getting into the actual center of the screen, where it's just 0 and the just well 0 0.0 minus um, this plus radius plus y. And now you have the local space over here, local UB, well, UB minus center, and you have the ball be placed with the circle radius and bit so width. I have it. And now you can actually place the color over here. Color with vector ball, and you do the same thing that again that you did for the other example. And you have it color 1.0. Oop, float. Hmm. Oh, semicolon. Back to no matching overload for back to then for color flat color. What? Oh yeah, there we go. And now you can see it bounces. We were trying this earlier where, for example, you wanted to bounce the thing on more stuff, to wanted to go up instead of more down with the kinetic energy loss. You can just do this where it's just going really up. It's really bouncy. You can see where yes, because it's going with 1.01. And for example, if it was going like this, it would lose a lot of energy right now. Where it's yeah, just that. And yeah, that's the another example. And let's actually present. Um, so everybody understood that example, right? Yeah, I love physics. For now, uh, I want to have the wrap up example for games where I have Rocket League over here. This is one of my favorite games. This is a mechanic. If you are not familiar with Rocket League, this is a mechanic called the cutter pinch, where it's basically getting into a really specific angle to the car and the wall to actually hit the ball really hard, as you see right there. And I see this as a lot of math on my brain, as I told you earlier, where I basically have the same vision as my dad, where he's seeing a lot of vectors. And I think this is where come back, where you can see the car actually have the vector that you need, and the normal vector that you have from the wall hit on a specific angle to create the velocity on kind of like a pinch over there. And it creates a collision where it creates the time window that you can see the ball to actually accelerate in a lot of speed. Momentum directly changes and all that stuff. Um, for the next one, I knew you guys would like that one. If you've been to a hackathon recently, you have seen a lot of 11 labs, like a surprise and whatever. And you see that if you are not familiar with 11 labs, it's basically getting into a voice agent AI, where it's basically getting into a lot of cool resources, kind of like making voices similar and all the stuff, making, for example, you need like a grandma talking about something, or you need Peter Griffin right there. Um, you can make it, and I think that one thing that it does really well is the aspect of the math, where you can see the vectors actually make it like a way to get into what you want, kind of like a manipulation of what you want, and determine what you actually need. And one example that did this really well, um, is one where basically one of my friends, for a hackathon, he made like voice pilot, um, in Unity, where it's basically just getting into more practice into piloting. And I thought that was really cool. And it utilizes math in a sense where it determines the actual pilot. You can set it to different uh, pilot type of stuff, where you can get it uh, for example, one thing that a pilot where it has from another accent or another country. And I think that was pretty cool, where it's actually getting the voice of people that are actually talking into um, a lot of things. And it determined to different ages and genders and all that stuff. And for graphics, right there, I have my 6, 7 cars on Lightning McQueen wins over here, you can see.
I was there when he took his
And this one of my biggest inspiration for getting into graphics, because I saw this one article that Disney made that it was pretty cool. Uh, that it was basically getting into how ray tracing actually was really useful in the Cars movie. And I think that uh, it is a great way to see how it is positioned, how lights are actually useful, and the and I would like to put this article really well up to standard. And in terms of, like, for example, matrices that you see right there, it also help with visualizing the world to actually be placed in, for example, you needed to place something right here or something like that. It was actually really useful to do that and to determine the position and scale. And right now, I would like to have great resources for you guys, for beginner stuff. I would say this is the biggest one, where you actually learn a lot of the basics math, and you gradually get better into it. And if you want something more visual, I think Scratch a Pixel, it's a great way to actually learn a lot of this stuff. And for more intermediate ones, I would say that these are the best, where these two are more into linear algebra altogether, where you actually see a lot of the graphics and games and a lot of stuff based on. And this is more general for computer graphics, but it's a great way to actually get into the math, I would say. I left a link for this one because I could not find a link for this one and the other two, which I should have. And for hard, For GPU jams, I think this is a big one. This for NVIDIA. There are multiple editions. I think these are pretty cool. And you actually get to learn a lot more into GPU programming, as well as some math that is actually useful. And for oh yeah, I forgot about this one. Game engine. If you want to make a game engine and the math that it needs, the physics and something like that, it's a great way to get into. I would love to get into this one, uh, and I yeah, simply it's great. Um, and you guys have any questions?
Are these slides going to be available
Yes.
on the site?
They'll be in the same place where the links are.
Yeah. Please fill this feedback form. It's so awesome. We need feedback. W feedback. Fill out the form, Eric. Fill out the form.
I'm giving you a form.
Yes. And yeah, we have our socials. We lucky did not post on Instagram for this.
My bad.
Yeah.
W outreach, man. W outreach. Nice.
W outreach. And thank you. I love GPK. Yay. Awesome. Thank you guys.
And next up, after not today,
We got the challenge, the monthly challenge
yes,
to end
the
up. Yeah.
challenge. If you guys are interested, I'm working on some stuff.
Yeah, same.
I'm gonna do my own thing, but there's a
I'm gonna do my own thing.
there's a thread. There's a thread. It's cool. No one's really done anything yet, but I'm gonna post something because I've been bogged down. I feel like everybody's just been kind of bogged down. People
Yeah.
getting sick, people getting bogged down these past 2 weeks, but month's not over. So lock in, twin.
Twin.
This is a monthly challenge thing?
Yep.
Yep.
Space themed.
Yes.
Space?
Literally anything. You could
You
do
can
like
interpret it however you want.
Yeah.
pretty much. Like, or I think we said outer space. So I guess
Yeah, outer space.
Oh.
you could
Same
like.
thing.
I mean, honestly, you could do whatever you
No,
want.
that's fair. That's fair.
Yeah,
Um,
let me stop recording.